of the atom?
Sure. But if it was heading towards tetrahedral, as they got further away, you'd think it would approach the tetrahedral angle, if the tetrahedral angle were the proper limit, but it's going down towards 90. And if we looked at the oxygen column, we see the same thing, where it starts off at 104 degrees and then drops down as you go down the periodic table.
So I'm going to speculate that because the bond distance gets longer, now the hydrogens can move closer together without the hydrogens themselves starting to repel. And so they want to get away from that lone pair on the top, if you sort of think about the lone pair being on the tetrahedral thing. And with ammonia, they can't get far enough away to do that, but by the time phosphorus or arsenic.
So an increased repulsion.
Because they are far enough away to distance-wise that you don't have the hydrogen repulsion on the bottom that you would have with ammonia, where they're closer. The hydrogens are closer to one another because they're not as far from the nitrogen.
What would you say would happen to water if we used a, say, 1.5 angstrom distance?
Presumably it would push 90, if my theory is correct. 90 degrees.
Well, but if you're moving further away, I mean, the lone pair hasn't gotten any bigger. And if it's further away, it's further from the lone pair. And if it were heading towards tetrahedral, then by being further away, that it would go towards the natural angle.
Yeah, but I guess what I'm saying is I feel like the lone pair would like to have a bigger effect on ammonia or water than it does. But the fact that the NH or the OH bond distance is so short, it can't. And so it's just allowing us to see how big that lone pair effect would be if we didn't have the other. That's my hypothesis. Clearly you don't like it.
Yeah. As you go down, and we can look at these. As you go down, the lone pair actually shrinks, and it's smaller as you go down. I would say you're right in the sense of the hydrogen, but the challenge I think is that in like nitrogen atom, there are 3 p orbitals at 90 degrees. And so the natural angle really isn't tetrahedral. The natural angle is 90 degrees. And the hydrogen repulsion pushes them away from each other.
I'm having trouble with your choice of the word natural, since I sort of say that's just our mathematical choice for how to understand something.
Well, except that the 3 p orbitals on an atom are perpendicular to each other. They are at 90 degrees with respect to each other, right, in the atom.
What's our experimental evidence for that? Not theoretical evidence, our experimental evidence for that.
Actually, I would say electron density maps from high quality X-ray crystallography, particularly of the heavier elements. And experimentally, we know, that nitrogen ground state is quartet S. We know it's an angular MMS. We know it's quartet from magnetic field effects. I think it's pretty well founded that, angles, that the p orbitals are at 90 degrees with respect to each other. And then d orbitals have interesting characteristics that are a little bit more complicated. But then and if you look at structures of, in particular, radical species as opposed to closed shell molecules, you get a better idea of where the unpaired electrons are in those. I would say both geometrically and then, from magnetic data. Okay, so before we go to the PowerPoint, the next thing that was your assignment was to look at some. I'm going to reload this. Let's bring in one of the. So at the bottom, we have the total energy as a function of iteration number. And this is a fairly typical sort of curve where the energy drops down and you plateau and you get to the final structure. We can look at, bumps along the way where, it got too close, but then it went back. This is a T conformation of benzene. When we're done here, we'll look at the electrostatic potential map on this to be able to see that in the center of the benzene centroid, there's a little negative charge, and that on each of the hydrogens, there's a little positive charge. And so it's perfectly reasonable to think about benzene putting a positive hydrogen into that negative charge in the middle. And so the T-shaped structure for benzene dimer, makes.
We can put that hydrogen there without being perpendicular to the
Sure. And in fact, that whole surface is really pretty soft. This is the one. Okay, so this is the other PBE structure. This is a parallel displaced structure. Started off with the two benzenes displaced with respect to each other. And there is, arguably this might have been starting with them just a little bit too slipped, but anyway, a parallel displaced structure. And then if we look along the time course of the optimization, we can see that it doesn't like what we started from, and it actually goes to a T conformation. In this case, a T conformation where there are two hydrogens pointed down at the alternate benzene ring. Gosh, when was it? 1989, I had a postdoc who was looking at aromatic interactions and proteins. She wanted to have a good starting point to think about it, and so she fired up Gaussian on benzene dimer with a fairly big basis set, and basically saw this event happen, which really discouraged her because this took back at that point months of computer time to crank out, and basically it went away. And let's get one up that. Let's go back to the starting. So this confirmation of benzene dimer, which is a perfectly reasonable confirmation of benzene dimer, the interaction is not dominantly, or can't really be dominantly, electrostatics. You can have a little bit of the positive charge interact with negative charge, but it's a confirmation that is really dominated by dispersion or van der Waals forces in terms of what's holding it together, as is the structure of graphene. This functional that we're using has no dispersion in it. It has no van der Waals in it, and so in fact, it can't find that confirmation. That confirmation is not a stationary point on the system. So the three functionals that we used this 8 PBE. We used B3 lip, okay, and I don't have the results for B3 lip, but from B3 lip, it's also going to not stick in this confirmation. And so the other one got done in like 12 iterations, and you see this goes on for hundreds of iterations trying to find its way to this other confirmation. B3 lip is going to do the same thing in the parallel display structure. Of the functionals that we used, the last one was APFD, where we said last time the first three were author names. This last term is dispersion, where a dispersion term is added to the density functional to account for the fact that one can't get at dispersive interactions very well with density functional theory. Yes?
So this demonstrates, I don't know if I can say equilibrium, but I understand we have the two benzenes, and like you said, after a period of time. So is that where it would kind of be an equilibrium, I guess?
Well, the equilibrium geometry for this functional, this isn't a minimum, and this is just marching along, watching the energy as a function of trying to go down to the minimum. So at each step, it evaluates the derivative, trying to head down in energy, and rolls around until eventually it ends up in that T-shaped confirmation. Where for this functional and this, if you will, initial confirmation, we end up with this. We end up with this. We end up with this confirmation or configuration as being the lowest energy configuration. The other calculation that started in the T shape, it ended up with just one hydrogen pointed down. There are, depending on method, a goodly number of confirmations that are accessible, 1 down, 2 down, a bunch of different orientations that are all rather close together within a half a kcal of each other. And so, but for this case, from where we started, we went to this confirmation. Not to say that this is necessarily the lowest one, but I would imagine, because I would imagine the one with one hydrogen point down is just a little bit lower in energy for this functional. If we did the APFD functional, we would find that both conformations are minima on the potential surface, and the parallel displace is essentially the same energy as the T-shaped conformation.
So would these spikes say at a point where the energy is high?
Yes.
Yes.
Yes, so this is the energy. And so it's going along, marching along, trying to go downhill. And as we so we start off, say there. And that basically wasn't a big bump, but it's bringing them too close together, running into the wall. And you know, it has energy. It has analytic first derivatives of the energy of the change in energy with coordinate. But the second derivative, which if you were to think about a harmonic to get down to the bottom, you need the second derivative information. It has that as a numerical estimate. It's not analytic. If you actually just hit a Morse potential and had the derivatives, you'd find that even with the second derivative, you don't go down to the bottom really very quickly. You oscillate on the optimization. But it would be nice if it always just went downhill, but it doesn't, even on something as straightforward as this. Okay, and so there are in Gaussian and in other electronic structure packages, there are a number of functionals these days that do have the dispersion correction. Technically, it's a pretty, so in density functional theory, we blasted through this really quickly, but the electron correlation term that we used, or that is used, is electron correlation between electrons of opposite spin, not electrons of the same spin. And this dispersion is actually electron correlation of the same spin. And so it's just not in the model at all at this point. And what's done is a 1 over r to the 6th term is basically added on to account for it, but 1 over r to the 6th goes streaming down. Problematic. If you just use 1 over the 6th, you'd end up with nuclear fusion, and that's not good. And so what they do is they go down, add on that sort of a switching function, and they have it go back up to 0. So it's turned on out in sort of non-long regions, but then it's turned off as you get in closer. And each way that people do that ends up with a slightly different result. Some you'll end up with sort of a corrugated surface. It's not smooth, and that's somewhat problematic. But they add on this 1 over r to the 6th, and so for someone who does electronic structure, it's a little embarrassing that you spend all of this computer time evaluating these billions of interactions, and you add on 1 over r to the 6th, which you can do on a piece of paper, and you add that on to get a reasonable answer. But that's just sort of where the state of the art is at this point. Okay. So, want to get back to thinking about this nitrogen, phosphorus, arsenic case. And we mentioned yesterday that the Pauli principle electrons spin, and we'll see that actually is the source of this repulsion between the hydrogens in our small models, we tend to talk in general chemistry about electron-electron repulsions as being electrostatic in nature because that's easy to think about. It's just 1/r repulsion between like charges. But for these steric interactions, the 1/r is way too soft to actually give that sort of contribution. And so last time we mentioned that wave functions have to be asymmetric. So if we have two where all we've done is switch the orbitals that electrons 2 and 3 are in, going from the first wave function to the second wave function, then this changed wave function, because of the symmetrizer, the Pauli principle, it has to have the sign change. That's just a requirement of properties of electrons. And so we can use a permutation operator to generate these antisymmetric wave functions. And so if we started off with this model here, where when we permute it, if we start off with this model for 2 electrons in spin orbitals, if we permute it, then the first one changed, and then the second one changed. If we just had one raw function, if we permute it, it's not obviously negative. And so going from here to here, it's not obvious that this wave function is the negative of this wave function. Okay, it could be, but it's not obvious that it is. Whereas if we start off with this model and do the permutation, it is the negative of it. And if we plugged in saying that psi b was equal to psi a into our wave function that has the second negative term, then we can see that that's equal to 0. And so what that's saying is you can't place 2 electrons in the same spin orbital. The notion where putting 2 electrons in an orbital is coming from is the fact that you can't put 2 in the same spin orbital, but we have 2 spins. We have alpha and beta spins for the electrons. Yes?
And these psi's are solutions to the Schrodinger equation?
This is just a model. It could be associated with a converged wave function, or it could be just a model that you're coming up with. In all cases, the wave function has to be antisymmetric, or it's not a valid wave function for electrons.
So would that be considered trivial? Is that why when n equals 0, that's why we know it can't have the same spin?
Well, let's go on to the next. So we can't
put. There's a missing tau there. The very last one.
Excuse me?
On the very last line.
Yeah.
So if psi b equals psi a, then tau operating on psi a would be. Is that no?
So
okay, never mind.
It's if because we take these permutations, if the wave function is antisymmetric, we're going to always, for every pair of electrons, we're always going to have the permuted combination of spin orbitals, and all of the ones where that you're effectively permuting in the same orbital go away in terms of spin orbital. Okay, so what if these spin orbitals are not the same, but we let them overlap? Okay, so if we started off with A and B being orthogonal, and then construct another orbital that adds on a portion of A to it, so that they're not orthogonal anymore, the overlap between them would be this term, which is 0, plus lambda times this term, which is 1. And so the overlap between these two wave functions that we're looking at are the overlap is this lambda term associated that we got by construction by considering this psi c to be the original b plus a bit of a. If we then look at this wave function that is antisymmetric, where we have the wave function, we permuted the electrons, and we changed the sign for the second term. If we take that and plug in what we defined psi c to be, then and expand it out into the 4 terms, we see that this term and this term, the overlapping pieces cancel out, and we're left with our original orthogonal orbital picture for the wave function. And so what this is saying is that overlap, which we could have between orbitals in a antisymmetric wave function, gets projected out or removed by the antisymmetrization process. You could go ahead and do the calculation over these non-orthogonal orbitals if you wanted to, but within this determinable model for electrons, all of that extra work that would be involved just is for naught, because the antisymmetrizer protects it out. Which, another way of saying that is it's not an approximation to take spin orbitals as being orthogonal to each other within a determinable picture. We can take them as being orthogonal. If we took them as not being orthogonal, the energetic consequences of that orthogonality are going to come through. Okay, that they'll be there whether we took them as being orthogonal or not. Okay, so what that says for if we take our nitrogen, phosphorus, or arsenic atom and thought about bringing up 3 hydrogens to it, we start off by bringing up 1 hydrogen in terms of we're thinking about individual spin orbitals. We bring up 1 hydrogen to this, and we'll ultimately bring up 3. If we bring it up along, let's call this the z-axis, then this spin orbital and this spin orbital, in general, would overlap or coming at each other. This orbital and this p orbital, the overlap is 0. This s orbital and this p orbital, the overlap is 0. And so the perpendicular p orbitals don't have any overlap issues. This one, we said we have a spin orbital psi a. I'll call it Vp, but that's the spatial, and Pz. Give it an alpha spin, because for spin orbitals we have a spatial and a spin part. This we'll call V1s, and if we give it a beta spin, okay, alpha and beta spins are orthogonal, and so these spin orbitals are orthogonal to each other, while the spatial orbitals don't have to be. Okay, so it satisfies the Pauli principle in terms of the antisymmetrizer, but it leads to a bond between the p orbital and the hydrogen. If we did this as an alpha spin, then we would have to make these 2 spatial orbitals orthogonal to each other, or the overlap between them is a repulsive interaction that raises the energy. And so In terms of spin orbitals, pairwise, we can have orbitals that have opposite spin and overlap. Beyond that, you can't. But so we can draw a bond there. And then if we bring up another, say, p orbital here, and we make a bond here, this s orbital, as it's coming in, this s orbital that's coming in is orthogonal to that p orbital. It's orthogonal to that p orbital. It's not orthogonal to that p orbital, but it's going to make a bond there. Okay. We could bring in the third one. And in terms of the interactions, again, it's orthogonal to the perpendicular p orbitals and overlapping the one p orbital that's directed at it. And so bringing in those hydrogens, okay, the interactions, and there is the 2s orbital, or 3s orbital on phosphorus that's going to play a role. But the dominant interactions are with the p orbitals. One thing we haven't talked about at this point is the interaction between the various hydrogens with each other. And they have to be orthogonal. These orbitals have to be orthogonal. And that orthogonality is an exponential dependence on distance. It goes up as the two atoms come close together. If it were a 1 over r electrostatic repulsion, it would rise quite a bit more slowly. Okay, so we trying to think. Okay, so what? So I've constructed a water molecule that has the usual commands at the top, except there's one additional part which is hard to see because it's in blue. So we have the pound p, then we have opt, except we have opt equal mod redundant, and that mod redundant allows us to add additional information to the file or to the structure, and the additional information that we're adding is these two lines down here, where you can tell, if you have, like, say, benzene dimer, you're constructing these internal coordinates, bond distances, angles, and torsions that you're going to use in optimization. There isn't any coordinate between the two benzene, but if you're going to optimize in those coordinates, you need one. And so it goes through and Gaussian goes through and adds an additional bond distance, angle, so forth, associated with the interconnection between them. Sometimes that can get pretty, sort of ill-defined, and you can help it along by saying, well, okay, these non-bonded distances are the ones I really want. Okay, so you can augment your representation of distance and angles by additional ones. We're doing that here. The B stands for bond. So there's bond T, I think, is for angle, and then D is for dihedral. But you can add different terms where we're saying, okay, there's a bond between atoms 1 and 2, bonds between atoms 1 and 3, and the F says we're going to fix or freeze those distances to the values that are in the input structure. And I constructed the input structure such that they were 1.5 angstroms away from each other. And so we've taken the water and we've stretched the OH distances and going to fix them at that. And we'll let, if you will, the one remaining degree of freedom, the angle, we'll let it vary starting at 104 degrees. We'll let it vary and relax to see what it wants to be, as if it were a H2S. Does that make sense? Yeah.
Okay, question. So you had bond and you had 1, 2, and then 3 is fixed. So 1 and the 2s, those correspond to what?
The atom numbers.
Okay, just making sure.
Yeah. And so, yeah, in a big molecule, you may want 85 constrained to something else, or you might want some specific angle.
Okay.
Yeah.
So, wait, sorry, one more question. So atom numbers, it just reads the numbers down the line, so it's not actually.
And unlike a lot of languages, it starts at 1, not 0.
Okay.
Okay, so, you know, things like if we're doing exactly the same thing in the ORCA electronic structure program, we would start at 0 instead of 1. And if you make the mistake, you end up going off and doing something that you're not happy with. But yeah, so this is a one-based world because this is Gaussian is a Fortran program instead of, say, a C program. Now, yeah, I mean, that's just, you know, they could shift the numbers so that you would start with 1, even if it's internally doing 0, but that's not the way people think. You have a question.
Yeah, is that file available on the cluster just to see the structure of it?
It will be in a few minutes, assuming I can actually do the transfer correctly. So, SCP. I'll just put it there for now. So they have access to the space, or should I copy it somewhere else? Then we will access it.
You can copy it from there, but I can put it on there.
Okay.
Where do you want it? Do you want them to each have it in their directories?
Sure.
I could put James at day 3 folder.
No, I think it would be.
That would be the great place. It's your great meeting.
So, as yesterday, we're in this day 2. We have this Gaussian cluster job, which you're all familiar with, having crank through some of these now. Um, edit the files so that we're going to read in that H2O long and then output a log file with geometry optimization results as we go along. Waiting for it to get out. Oh, I'm waiting
Oh, yeah.
for it to get out of the VI. You also have experience with that. Yes.
It was under the file of the water molecule that gave the coordinates. And at the bottom, you were talking about the B12F. So looking at that, so does that mean the bond 1, 2 is fixed?
Yes.
And the bond 1, 3 is fixed?
Yes. Yeah.
We're allowing the other one to fluctuate, is that right?
Well, in this case, there's only one other degree of freedom, and that's the angle. And so it's, not it hopefully won't take more than a few steps to be able to find the best angle. This may have been a mistake. I probably should have just catted it. Okay, so these are, it would have made connections between those atoms anyway, but what it would not have done by default is freeze them, force the coordinates to be the same. It does that, it's like, okay, so there are a variety of ways to provide a constraint, right? You could add in a really strong stretch term that would freeze it, or you could project out of the derivative matrix that component of the derivative, and so there is no derivative, and that's what they do, is they remove it, and so that when it's optimizing, it just doesn't feel the force that would normally drive it together. And so for each, so there's different kinds of constraints that one can apply. And I'm hoping that there's one blank line. So each of these segments of input is separated by a blank line. And so there's one blank line. Should be one blank line between each of the segments and a trailing. If I didn't make any mistakes, this should go off and run rather quickly. Just ran tail to look at the end of the file, and we got our little same, and so it ran successfully. It didn't error out. And so, rather than opening the file or whatever, if you just tail the end of it and you don't see a saying, then there's an area that you need to go in and do something else. So
Is it because we're doing it through Gaussian that it's the S batch? And because I know previously we've done Python and then
the Python is invoking the Python interpreter sort of interactively. This S batch is taking your job and instead of running it, sending it off into a queue to compete with other jobs to then run sort of in background on different nodes. Other things happening on there, but yeah.
You could run Python the same way. You just put it in you could put it in a job file and dispatch that job. The Python jobs that you guys are running are so non-CPU intensive, they're very quick. Whereas these Gaussian jobs are very CPU intensive. So if you imagine that what people are logging into is a single computer, and if everyone was running Gaussian jobs on that computer, no one would be able to do anything. I mean, you can barely do anything as it is, but it'd be very slow because everyone would be demanding all the CPU resources. But that single computer has control of a bunch of other computers that are specifically there to run jobs, to run computationally demanding things. And so what that S-batch does is basically it's a program that assigns jobs to computers that this head node has control over. And it does it in an orderly fashion.
They're called schedulers. That's all we do, schedule jobs.
so does that mean worldwide people can send jobs?
Not to this cluster. I mean, so my cluster, this is what we're accessing here, is physically on the other side of campus. But it is its own entity. You can only access this cluster if you have an account on the head node. And then all of the, what are actually called slave nodes. Slave nodes don't have their own internet access. They're only accessed by the head node.
So you don't maintain hardware yourself.
Sort of. Yeah. I mean, I do have some system support. No. If there's hardware failure, then I'll have to go.
But you don't have any infrastructure as far as.
Oh no, there's a whole room. Power with cooling.
Air.
It's a whole room that has a bunch of stuff.
Okay, so here's our water molecule. The builder doesn't recognize bonds because they're an angstrom and a half away from each other. The energy, it took it basically 2 steps because it only had 1 degree of freedom. One would hope it could find bottom fairly quickly. And so that distance is 1.5. And now the angle is 91.3 between. So by stretching it out, those hydrogen repulsions went away, and we end up with this smaller angle. We could go through and calculate the molecular orbitals for this case to be able to look at what they look like in terms of the bonds. But one of the the homework assignment that you have for In the outline, we talked about doing transition states, but I think we're not going to do that quite yet in this course. But basically, to find a transition state, normally when we're doing an optimization, we're starting up here in some place, and we use the first derivative, the force, to move downhill towards a minimum. But for a transition state, what you do is you head downhill in all directions except one. And in that one direction, for example, if we were here, in that one direction, we're going to head up because we're trying to head towards a saddle point. If we just did a normal optimization, even if we started, say, really close, it would go down towards the minimum. But because we have this one imaginary frequency or one negative eigenvalue of the second derivative matrix, we'll march uphill along that one direction to find the transition state. There are a lot of different algorithms out there for trying to find transition states. There's a rubber band technique, and you interpolate between reactant and product coordinates and go up over some path. When you get beyond simple molecules, the coupling between the stretch band torsion and so forth makes it a little problematic. And so what we tend to do is guess really good, and then use the analytic second derivatives at every step. Calculating the second derivatives takes quite a bit longer than calculating the first derivatives, and so most people will do these things where you do a constraint such that you don't need the second derivative information. But there are so many examples of that giving you wrong answers that we go ahead and every step calculate that second derivative matrix and just pay the extra time to make sure that we're marching up towards our saddle point. Once you've found a minimum as in all of the first derivatives are 0, you can start from there and head down along the imaginary frequency and march towards reactants or products to make sure that you really did have a saddle point. But because we have been spending so much time thinking about spin, the homework assignment that you have is going to be looking at a molecule. Each one of you is going to be looking at a molecule that has some unpaired electrons in it, and so you can see what these orbitals look like in the case of, or what the electron densities look like in the case of a system with unpaired electrons. And so what you're going to ultimately be plotting is for our wave function, we can separate them into alpha spin orbitals and beta spin orbitals, okay? And then we can calculate the alpha electron density as the sum of the product of the orbitals times themselves, and the beta spin density for the beta electrons. And then what we're going to be looking at is the net spin density, where it's the difference between the alpha spin density and the beta spin density. And so we'll end up with positive contributions and negative contributions to our density generate a cube, and then we can plot this cube that is this net this difference between the alpha and the beta spins. Orbitals, things that we've looked at, and actually I don't think we've actually plotted any orbitals yet. I forgot to do that. Orbitals, particularly orbitals that we've looked at that are obtained by solving the variational equations for a single determinant, those orbitals can be mixed with each other without changing the energy of the system. And so they're a really nice sort of visual construct, but they're not a physical observable. Spin densities, on the other hand, are an experimental observable, both directly and then through magnetic interactions. You can actually, they're, if you will, more real. You can take this spin density and have it expressed over your basis set and diagonalize that matrix to get orbitals that are the representation of the spin density. And those are spin natural orbitals, and they have a precise definition. You can't interchange them without affecting property. Yeah.
Experimentally, you said we can physically see them?
Yes.
What do they use to be able to? Is it like X-ray?
You can get at for AFM information. You can get at the total density, but what you in building in like a magnetic field effect, you can actually get at spin differences. In ESR spectroscopy, the scalar coupling interaction between a nuclear spin and the electron spin, you can measure the ESR spectrum, and so you can get at those coupling constants and as a measure of spin density. Numerous other, because spins interact with magnetic fields so well, numerous other magnetic spectroscopies will give you a measure of spin density on a given nucleus or a map of it. Okay. So we'll go through and do one, but basically just the first column. Okay, we're just going to do cases where we have an upright electron. I'm not going to attempt this half quite yet. The builder's not really up to the task for helping us construct a good guess for that. But
I just sent you the slides to PDF, so you have those. That assignment is the last slide.
and so what we're going to, so again, you build a molecule and then run it through Gaussian. The builder doesn't tell it that there's an unpaired electron. So if you just run it through, the builder's going to come out with a file with 0 and 1, 0 charge, singlet. There's one unpaired electron, 1, 1, 1, 1. And so those are all doublets. And so you put a 2 there. This one, sorry, it's a little bit different. This is alphabetical. It wasn't being prejudicial. This actually has 2 interesting electrons. And we can go through how to get that picture later on. It's not a simple radical, but it's a diradical kind of species. Okay, so force of habit. Rather than going through a builder, I'm just going to go ahead and modify our little water example. Where, again, now it's going to be radical because I'm going to get rid of it's waiting. Knows where I'm going to end up. I'm going to just blow away one of the waters, or excuse me, one of the hydrogens, and then blow away the constraints. So we're just going to do hydroxyl radical. See if I can get away with typing ahead. Yes.
You can avoid this delay if you do editing of files in your home directory. It's just this slow between the head node communicating the Lester file system.
I wasn't quite out of there, unfortunately. Okay, great. Okay, so now Oh, shoot. Yeah. And then over again so we can get a checkpoint file. Okay, so now we have a checkpoint file. It has our wave function in it for hydroxyl radical, and we want to generate a spin density plot. First thing, again, we need to generate our formatted version of the checkpoint file. Okay, so now, again, the we have one unpaired electron in this plot, and so we need to, we're going to transfer this spin density cube file back to our local directory and then be able to display it. Okay. So now we'll open up the cubes rather than the computation one. We'll load a file. So we'll load this spin density file that we created. And just I'm going to display a value of, again, of the surface, and the value that I like is 0.003 for the a density plot. Aesthetically, it looks about the right size. Okay, that's great. You see a nice p orbital that's showing up. Except that if it were to show up,
You want to use Gaussian?
excuse me?
You want to use Gaussian?
Sure. Is it on here?
Just go to the directory and then go to the terminal and just type GB. Just type GB.
Okay. So, I know you're thinking to yourself, I know a p orbital looks like that, right? This isn't the orbital, it's the density. So it's psi times psi, and so that minus sign basically goes away, and so it's positive for both lobes. But you're saying to yourself, I see a different color there too. It isn't just all blue. We have a little green over here on the hydrogen. If we rotate that around, you can see that that green is perpendicular to the plane of the OH, okay? And that is called, really original name, spin polarization. That singly occupied p orbital asymmetrically impacts the OH bond, and you end up with some spin polarization. So if the
What do you mean by a perfect plane of the OH?
well the
OH is
the line of the OH perpendicular to the radical plane. So the radical, right? So if we have a p orbital here, and the plane perpendicular to that is where the green is. Okay, and that polarization, because if you think about hydrogen and p orbitals and not much there, if you were thinking about the spin density associated with hydrogen, you'd say, there really isn't any. But if you actually look at a molecule with an paired electron, you see spin density on atoms that you wouldn't think otherwise would have it. A significant amount of that is the spin polarization effect. The fact that alpha spin excess here, beta spin not, and so that there can be some leakage of the opposite spin that shows up, and experimentally you can see it in the asymmetry of things like scalar couplings that become tensors and so forth. But so in principle, assuming I can figure out what went wrong with the builder, in principle, by the time you've built the molecule and got your spin density, you should be able to read it in and have it display and be able to see sort of the spin density in these different molecules. And so if you basically cut and paste the image, I'll build a little gallery of these spin density plots for these different types of molecules. Questions? If not, then tomorrow we'll start in on we'll start in on excited states.